Java's Genesis sequence.
Hi everybody and welcome to this presentation. I'm Per. I work in the Java core library team at Oracle, and today I'm going to talk about performance update of what we did this year. So Java is faster than ever. I was here last year and then I claimed with Java 21 your code runs even faster, but I guess this is no longer true because if you run under 22 or 23, 21 is slower, obviously. Okay, so I'm going to talk about some of the OpenJDK products that we have, then discuss some metrics around performance, discuss a little bit of the challenges that you have when you do performance improvements, talk about some of the tools that are available to us, and then after that I'm going to talk about 5 recent performance improvements that we did in the past year. And then at the end I'm going to discuss what's ahead of us, what are we doing in the future to improve performance. And then how you can test your own application with these new features and see how fast your application is going to run under a new Java version. Okay, so we have a lot of things going on within the OpenJDK projects, open community. We have Amber, which is producing a lot of new language features. And I think many of these features might not improve performance that much, but it might nudge you towards writing something that is more clean and it can have a secondary effect that it will eventually run faster even still. Then we have product Babylon, which is a bit maybe obscure for some people. Babylon is about code reflection. And what is code reflection? Well, we have reflection today. We can see what is the type of this field, what are the methods, parameters to this method, and so on. But with Babylon, we can actually analyze our code. So we can express some logic in Java, and then we can do some transformation and write maybe GPU code and run that on a GPU with thousands of CPU cores. And that will certainly have an enormous impact of performance. We have Leiden, which is the title I spoke about Leiden, I think it was yesterday. And with Leiden is aimed at improving startup and warm-up time. So already today you can use something called a CDS, which can improve your startup time by a factor of 2. But with Leiden you can have maybe a startup time of a factor of 4. And you eventually will get also warm-up much faster than you can do today. Then we have product Lilliput. I'm going to talk about a little bit about that specifically, so I want to spoil the fun thing here. We have Loom, which is lightweighted threads, which increases the scalability of servers. So now, before you can only have so many platform threads, but with Loom you can have millions of them. We have product Panama, which I have been engaged with in the last 2 years. And we delivered the FFM function, foreign function and memory API in Java 22. There is also another initiative under Panama, which is the vector support, which allows us to use SIMD instructions directly from Java. And I will talk about some of the improvements we made there as well. We have Valhalla, which has been going on for decades, I think. Brian talked about that earlier today. Well, the title is Code Like a Class, but works like an int. So eventually we will be able to use those wrapper classes and abstraction, but they will have the same performance as a primitive type, basically. So that will certainly have an effect on performance. ZGC is another thing I'm going to talk about more thoroughly in one of those 5 highlights I'm going to do later on. So let's look at performance. It sounds very glorious to be able to just sit day after day and just trying to fiddle around and get better performance. But it's actually not that glorious if you think about it. So we have to prepare for an upcoming feature. We know where Java is heading, and maybe we need to prepare for those things that are going to coming later on. So it won't give you any benefit today, but maybe in 2 years. We have to fix regressions that we call it internally. So if you do a change, you might end up with that. This wasn't really so good, so you need to fix that. Users are getting back to us and said that I'm using this in this very particular case, and the performance wasn't really what I expected. So we need to figure out why was that the case. And also we need to leverage features that we recently introduced. So we need to go back and maybe rewrite code and then evaluate, did this affect performance? Did it become better or worse? So let's take a closer look at some of the metrics you can have when you evaluate performance. And we'll start with metrics in the temporal domain. That means in terms of time. So I think the most common way to measure performance is average throughput. How many operations can I do per second? Or how many megabytes can I chew through per second? But you can also look at the typical latency. So if you make a million experiments and you sort them in order, and then you look at the middle, that's my 50% percentile. That's not typical latency. That's another thing. And then you can see what's the worst case. So you can call this, exotic outliers. What in the 99.99 percentile would the worst result be? Or maybe you have 5 nines or so. And it turns out that maybe if you sacrifice the average throughput, you will get better figures for the worst case. So you have this kind of trade-off in that case. And then you have all sorts of combination of these. You can say that I want at least this, but I want the throughput to be at least that, and so on. Okay, then we have more indirect temporal metrics, which I touched on before, which is the startup time. The startup time is the time from when you start your application until it produces actually some useful work. And more realistic, it's like if you deploy a web app, it's the time it takes from deployment until it can serve an incoming request. Warm-up, on the other hand, is the time it takes before an application actually produces peak performance. As you might be aware, Java will kind of interpret your code before when it starts, and it says only after so many invocations that your method is actually going to be compiled. And so it takes a while for them to warm up. And that typically measured in seconds or 30,000 operations or so before your method gets hot and gets compiled by the JIT-complier. Then we have resource metrics. Maybe your method is using a lot of memory. We all know that different sort algorithms have different memory requirements. The access pattern is a resource in itself. If I'm hopping around and accessing more memory in a random fashion, I will mess up my CPU caches. So that's a scarce resource we need to preserve. We have memory pressure. Maybe my method is allocating a lot of memory, and then that needs to be cleaned up. So that's also something that is a resource. The number of threads is a resource. If I have a sort algorithm, do I do it with one thread? Can I do it with many threads? And if so, how does that affect overall performance? We have CPU usage, cache locality, which it's very similar to memory access patterns. You can have contention around scarce resources or resources that are guarded by locks and similar stuff. The code size is another metric. You can write something very fast, but there is a lot of code going on, so that's a resource. SIMD is another resource. Maybe you have a CPU that shares SIMD implementation across several CPU cores, or need to throttle down the CPU clock speed when you're using SIMD operations. So there are a lot of things to think about when you are working with performance. Okay, I think something missed here. Resource metric. Okay, I'm not seeing the same. Okay. I think this is a very important thing, power efficiency. We know that power is expensive, so it's good that we can do many operations for the same amount of energy. It's not only that we need to produce that energy, but we also need to cool off the same amount of energy. Eventually, energy has to dissipate. The heat has to dissipate somehow, and that also costs money. Okay, so we need to consider what platform are we running on, what CPU type are we running on, what that CPU type has for retrieval versus computation ratio. Just accessing 64-bit memory today is 100 cycles. 25 years ago, ratio was more close to 1. So therefore, the algorithms today look different than the algorithms did for 25 years ago. We have different consideration of the number of cores. We have which GC are you using, which garbage collector is used, how are your thread used, are you using a pool of them, or are you creating them as you go? And then we have workload distribution. What kind of shape do your data has? What content is your data? And there's something called pollution, which means that you're calling a method with the same kind of parameters. Many times you get one kind of compilation, but then you certainly start to call that method with other kinds of parameters. And then, of course, your performance will not be as good. So that's called pollution. Okay, to summarize this up, we are usually looking at average throughput, which is operations per second. That's what we are mainly focusing on optimizing. And this is measured after warm-up, so we are not looking so much at compiled code. So this is compiled C2 performance, or GRAL compiler performance. And I think the mantra here is, if it ain't compiled, it's hardly used anyway. So it doesn't matter so much if you have a method that it's slow, if you only call it a handful amount of times. Whereas if you call a method 1,000,000 times, it's more important that it's performant. And of course, we do this for the supported platform we have, mostly Linux on x64 and A64. And then we have Windows and Mac. And I think the x64 Mac is kind of going away, and it's going to be more and more ARM. So this is kind of a positive feedback loop. The more you use a method, the more optimized it is, and the more likely it is that you use that method. Okay, so when you're doing measurements of performance, don't use a laptop. And I should be honest here, I used to use my laptop when I do performance tests, but you need to be very careful because the performance will be different if you have plugged in your power supply. If you don't plug in your power supply, the computer might throttle down a bit in order to save energy. The intensity of the screen might affect your performance and a lot of other things. And it's a classical mistake to run two benchmarks after one another. So you start off with a baseline maybe, and then you run your presumably faster code just to realize that it's slow. But it wasn't slow. The reason was that when you run the benchmark, you heated up the computer, so it needs to throttle down. And therefore, your second run was slower. So it wasn't actually slower, but it was slower because of the kind of heat depth you build up. So it's better to have a dedicated computer. You have to run the method tens of thousands of times before you're measuring. I can't tell you so many times I got a mail that people complaining about this method, it's slow, and then they just ran it for 5 times and say that it's slow. But that's not the way we work. We work with compile methods. Use system nanotime. So I know there is a method called system current millisecond or something like that, but it can actually go backwards because system millitime gets adjusted. For example, if you're using a time protocol over the internet. So this can create very mysterious figures. But nanotime is monotonic. It will always increase, and it's roughly the number of nanotimes since you started the JVM. The JVM is also very good at doing some kind of optimization under the hood, so it can infer constants, fold, and speculate on your code. So it might be the case that you're actually not testing the code for real. You are just, the JVM outsmarts you and inlines code, and you're actually not testing the algorithm as you think. So there are some tools, and I think the JMH is the most important tool. It's the Java Micro Benchmark Harness. We can help you with a lot of these things. So you can just annotate a method with the benchmark, and JMH will pick that up and run it for you. It properly consumes the result you return. So if you just write a method that returns an int and you don't use the int, then it can be the case that the JVM just throws the value away and it doesn't even invoke your method. But the JMH framework makes sure that you actually are calling methods and actually using data. It prevents inlining of input data, so you're actually testing the code you are writing. And it runs several rounds in separate VMs, so you can get a kind of idea of how much jitter you have. It adds a warm-up phase. You can decide for how long it will warm up before you start measuring, and it estimates error margins. So here is an example of a test I wrote that's actually sitting in the JDK today. So what I'm doing here is that I have a test of a fill operation. It's a bulk fill a memory segment. And I'm doing, you can see the param there. So I'm filling for different sizes. So I start off very small, 2, 3, 4, and so on. And then I just explode at the end. And then I have a bunch of tests. You see the 2 first one there. Sets up a system property and runs this method, and then sets a system property to another value and run the method again. And when I run this, I kind of get a status report of this. So I give this command, and after quite a few minutes, I get an answer here. So something like this. So the first case for heap segment fill, I get some values, and for the unsafe fill, I get other values. And at the far right-hand side, you can see there is a kind of an error estimation, which is, compiled using statistics of observed values. So this can give you an idea of was my measurement actually, relevant, and how thorough is it. And of course, you can export that, and there are different tools on the internet which allows you just to drop this in, and you can see what's the jittering and error margins and so on. And of course, you can also paste the values into a normal spreadsheet program and extract figures like this. Usually when we work with propositions of improvement, we have something called base, which is, this is how the JDK is today, and then patch is my proposed change. So in this case, we can see that the red curve here is the patch, is certainly better, at least for smaller values. In this case, and we're going to see more about this later. We also at Oracle have internal tools that every time we do a major build, we have, I think, hundreds of benchmarks that we evaluate every time on every platform. And we have people very carefully looking at this. So you will get noticed if you do something that will, impair performance. You will get a mail for sure. This shows an example of maybe a smaller test set. I'm doing something, and I have 4 tests called the user suspects there, and they are tested on all the platforms. And if it's something red, it's worse. Is it gray? It's like the same, and green are better. So this gives kind of an overview what my change actually did. And I don't have to test on my laptop. This is all dedicated servers, and it's even ensuring that I'm running on exactly the same instance that I ran the previous time, so you really can compare the values. Okay, now I will take a step back and talk a little about the circle of life of Java code. It's important to understand this when I'm going forward and talk about optimizations. So, as I mentioned before, when your program starts, the JVM is interpreting code. It's looking at every bytecode and see, well, now on this bytecode, I'll do this, next bytecode, and needless to say, that is slow. And while it is doing this on the so-called tier 1, it collects profile data. And there's an F there, meaning that we are collecting full profile data. Profile data is what kind of parameters am I using? How many times is us calling this method? And then we come to a next step. These are called tiers. So the first one is tier 0, and then we have tier 1, which I haven't shown here, tier 2, and tier 3, and then tier 4. Tier 4 is the most interesting one. It's the C2 compiler or the Graal compiler, which actually produces the most performant code. But we don't want to get there immediately. We want to get there at a good time. And a good time is when we have gathered enough profile data to make an educated guess how our code is actually run in real life. And so we can advance when we're going here to T3 and T3. And when we get to T4, we are able to look at all this kind of profile data that we have gathered. And then the compiler is allowed to speculate. If we have only called this method with a parameter that is null, for example, it's likely that it will stay that way. It's likely that it will be called with null again. So it can speculate and say that, oh, I assume that this parameter would always be null. And then it will install something called an uncommon trap. So it says that, well, if this is no longer true, I want to back off. And that is the optimize arrow there. And so it can, short circuit every if or switch case or whatever in there that we're checking this variable. So if it's non-null, for example, you don't have to even consider that. So that gives us great performance. And we are actually allowed to do this kind of speculation because we can always bounce back again, start collecting new data, and then we go back eventually to T4 again. Good. Okay, so now I'm going to talk about some of the optimization strategies that the C2 compiler can do. So I'm going to talk about inlining, loop unrolling, hoisting, auto-vectorization and the related superword, pre and post alignment, long to in loop conversion, and different concerns that might arise, for example, aliasing and control flow. And don't give up now on me because I'm going to talk about this individually on a separate slide. So let's assume we have this very simple program up here. I have a copy method here that takes an array and it takes another array to which is supposed to copy the contents of the first array. So I have a source and I have a destination, and presumably the destination is big enough to match the source. That's kind of an invariant here. And then I iterate over all elements, I set the values, and that's it. And then you can see the actual code down below. I initiate a source array, and then I have a kind of a blank destination, which is the same length as the source in this case, could be bigger. And then I invoke my copy. So the first line is inlining. So the compiler can say that, oh, I will kind of see through this and remove the method call and instead view this kind of instruction as a unit. So it will look something like this. I have a source, I have destination, and then they just start to operate them. So in this case, we have kind of eliminated the actual method call, which involves putting things on the stack and so on. I know this is simplification because anything happens, we still have to have the right stack trace and so on. So this is only showing the principle. Okay, loop unrolling. What is that? Yeah, you remember now that we have our inline code, but instead of doing a single operation per loop, we can do multiple operations per loop. So maybe we can do 4 steps instead of just doing 1, and then we can amortize the cost of maintaining this counter, increasing it and checking whether or not it's smaller than the source length. So now we basically do that every 4th time instead of every time. And then you notice that we have this kind of ... at the end. There is something we need to clean up there, a tail. It might not be the case that the source is evenly divisible by 4, so we need to put in some extra code there to handle the tail, but I haven't shown this in this picture, but it's important to remember that that has to be done. We have to do a mop-up operation there. So that's great. That will improve performance a little bit. So that's unrolling. And then we have hoisting. So if you look at this example here, you will actually see that the access to the source array will also entail an index check. If we are trying to, address this outside the boundaries of the array, there will be an exception, an array out of bounds exception. And the same for the destination. But we can hoist this out of the loop and say, we can check whether or not the source is greater than the length, and therefore we'll throw an array index out of bounds exception right away. And then we can, I have introduced a new semantics here. So instead of brackets, I use parentheses. And that means that I do the same, but I don't do any range checking. And of course, this will not work in normal Java program. This is just a way for me to express this on the slides. And of course, it's able to figure out that the source actually is using the source length. So we know that that is never greater than the source length because that's implied within the iteration. And we know that the length of the destination is always big enough, so we don't have to check that for every iteration as well. And this is hoisting. Okay, auto-vectorization. That's another thing. So before we handle this in data sizes of 1, but we don't have to do that. We can handle them in data sizes of long, for example, and then we can take bigger steps. So I've kind of added something, a method that does not exist in reality, but something that returns a view of this byte array and viewed as a long array instead. And then I can use steps of 4, data units of 8, I mean. And that is much faster than working with individual bytes. So that is auto-vectorization. But it doesn't stop there. Some of the CPUs we have kind of assembly operations that can handle much more than just 64 bits. Some of them can handle all the way up to 512 bits. And that is 64 bytes. So I kind of invented my own machine code instruction here and said that I can load 525 bits into a certain register that I call X from the address of the source plus my index. And then I store that at 256-bit from the address of the destination. And this means that I can work with even greater sets of data units, and that will be good for performance. So that's great. And then I can apply hoist and unrolling. So I can, instead of computing the address, I can hoist that out of the loop and only compute the address once. And if it's a heap array, which is this in this case, I need to pin it before because the garbage collector is now not able to move it around. And then I can unroll my loop and work with logger chunks. And in this case, I'm actually working with 256 bytes per iteration. And now we're talking about performance gains. And when everything is cleaned up, I can unpin my source and destination there. Okay. Pre and post alignment. So let's see, we have some kind of memory here, and I'm showing like 8 bytes here alignment. So we have something with hexadecimal, looks like 3 zeros at the end. So it's aligned at 64-bit boundaries. Of course, I can view it as bytes. So suppose I want to do an operation between the arrow indicated with begin and do something with it until I reach the end. Let's say I want to look for a null terminator. Let's suppose this is a C string. So what I can do is that I can start off with A, which is a byte. I can check the byte. Is this byte 0? No. I continue with B. Is this byte? No. And now I are on the even 64-bit boundaries. So now I can switch over and put in a higher gear and use long operations instead. So I can now read 64 bits in one chunk, and there is actually a clever way to deduce whether or not the long contains one of the bytes 0 in there. It's kind of a hacker thing to do that. So I can work with units of 8 bytes instead of units of 1 byte. And I have the cleanup operation with the tail, so I need to handle the last one there. And actually, this is something that you do today. This is the method I wrote a year ago or so, which is actually looking for, is it? No, it's not. Yes, it is. It's a string length byte, so it's looking for a byte there. And it's actually, you see the first point up there, that's the head. So I iterate using bytes, and then there is a middle part, which is using long steps, and then there is a cleanup at the end. So this is a clear example of post and pre alignment. Okay, long to int looping conversion. So there is something called memory segment, which is part of a foreign function memory API, which became final in JDK 22. And a memory segment is a description of 64-bit memory. A byte array can only be so big, like 2 gigabytes. But with the memory segment, you can have 64-bit addresses. And of course, if you want to do that, you have to use a long as an index when you iterate. Unfortunately, iterating over long is slow. So what you can do is that you can use 2 int loops instead and kind of chunk them up. This is a kind of a generic unrolling, you can say, or parametric unrolling. So you can have an outer loop that loops with an int, and the inner loop is using also an int. So this will give you some performance benefits. Okay, everything looks good, but then you run into problems. So we have a problem called aliasing. So suppose you have a source that contains the contents of some array, and then I have a destination which is the source, but shifted 1 byte. So they are actually pointing to the same memory, like this. So the source starts somewhere, and the destination has its 0 offsets somewhere else, but they overlap. So suppose we are copying from source to destination using bytes now, then means that we will take the source value of A and put that in the first bucket from destination, which is where source B is. So this will overwrite B, and so we will have an A in the next position again. Then we'll advance our pointer and go to the second in the source, which now is an A, and we will put that in the second for the destination, which now is an A, and then we will overwrite the C with an A. So eventually we'll end up with the source being all A's, and the destination will be all A's except the last one, which will be untouched. Or maybe not. Okay, maybe it will be an A there as well. But if we choose to copy in terms of 4 bytes, for example, then we will take A, B, C, D and put that offsetted by 1. And so the contents of source will now be A, B, C, D, which is not the same. So clearly we have a problem here. And that's called aliasing. And that is something we have to guard from when we are doing these kind of operations. Another concern is control flow. So while we are copying, we might have some kind of condition that says that, oh, I want to exit the loop if this condition is true. And of course, we can't use operations with logger segments. If we have a control flow operation, then we just back off and say that we can't do this optimization here. So with that, I will go into 5 recent performance improvements that we have done in Java 24 and 25. So 23 was just released September 17th, and we will do a fork of Java 24 in December, so it's not that far away. And when we do the fork, we know what we are going to have there. It's not going to be any more performance upgrades. And I kind of made an example here and tried to look at different things and not the same things in order to show you that we are working on several fronts. So the first one is MergeStore. Now MergeStore, some code look like this. So yeah, I have a long that I want to insert into a byte somewhere. And the way to do this is to shift the long. So in order to do this, I must have 8 shifts, and then I put them in sequentially into the array. This is a bit wasteful. Let's see here. You can use unsafe instead, or you can use a var handle. And there is also an internal collection of all those var handlers internally in the JDK, which unfortunately you as a developer can't use. But you can look there and see how it's done, and you can do the same way yourself. So it looks like this. You have a var handle for longs, and then you can actually just do long set, and it will do this in one operation for you instead of having to chop it up, because it's just one write. And this is something I spoke about last year when I was here, that we have in random access file, which is a very old class that was here already in Java 1.0. So we were able to improve the performance here by a factor of 8 by doing just this change here. But the new thing with MergeStore is that the C2 compiler, remember we have all the steps, so that the C2 compiler comes here, it will recognize this pattern, and it will do this automatically for us. It will insert basically just one machine code instruction that takes this long and just write it to the array. And that's pretty awesome, I think. Now in order to use this, you have to be a little bit careful, because if you do something like this, maybe you would like to insert a long and then insert other things afterwards. But if you are modifying the object offset here, I think that the C2 is not really able to establish that we don't have this alias problems I just told you about. And therefore it will back off. So it will not work if you are modifying the offset. So what you can do in that case is you have to keep this kind of static offsets here, and then you can increase the offset after you have done all these operations. Is there a merge load that corresponds to a MergeStore? No, there's not, unfortunately. So you have to use a var handle, and you can go and look into this class, how you can do that. Okay, next up is the foreign function and memory API bulk operations. So as I told you, a memory segment is an abstraction of a 64-bit continuous reading of memory, and it can be on and off heap. And with this segment, you can have several operations that does things in bulk. So you can fill it, for example, with zeros or anything else. You can copy it to another memory segment, and you can mismatch. You can have one segment and another segment, and you can ask, where do they mismatch? And if they don't mismatch, you get -1 back. And this is internally backed by unsafe, or I should say was backed by unsafe, which is mostly intrinsic and native code. And also you have every time you allocate a memory segment, it will fill it with 0 for security reasons. So it's not only these primitives, it's also other features that depend on them. So it's important that they are quick. But in a surprise move, we replaced the native code with Java, and it became much faster. So instead of using machine code or native code, just running with Java was faster. And how is that really possible? Well, it turns out in order to transition from Java to native code, there is a price to pay. So that is the reason why it's faster for smaller values. So that's quite interesting. And it turned out that the implementation in Linux A64 wasn't that great. So there was a substantial difference when you're running it under Java rather than invoking the native methods. So what we did was that we have a threshold. So the threshold was basically 64. You can see that's 2 to the power of 6 is 64. And if it was an ARCH64 for just fill, we had a much bigger threshold because this intrinsic wasn't that really great. And then we just did this. If the value is lower than the threshold, we do this by Java. But if it's bigger, then we just invoke this, scope memory access, which is basically a wrapper around unsafe. So that's really interesting. So this is how the loop looks like when we're doing data sizes of 8. Okay, and then the question was, when is Java slower than native operation? And in some cases, the answer is never. Java is always faster, for example, on x64 Linux. And we are working on improving this Java code even more. So we are thinking that in the future, we are going to bump up this kind of limit and remain in Java. And that's positive, not only from a performance perspective, but also we don't need to transition to native code and have this kind of checkpoint and pinning problems that we can experience for native code. Copy was similar. We had better performance for copy. In this example, it's A64 Linux. So we will have better performance there. Mismatch is the same. So you can see here that in this case, higher is better because we measure throughput. So even for smaller and bigger, and in fact for every case on Linux A64, Java performed better than native code. Okay, and there's more to come. We will improve auto-vectorization. We'll have better functionality. We can improve the thresholds. And eventually, we might be able to use the vector API when that becomes a preview feature. We can use it internally. Okay, moving on to next one is the secondary supercache scaling. This is another type of problem. It's something that was implemented for the JIT-complier, and it speeds up queries such an instance of expressions. So imagine we have a class called foo, which extends bar, which in turn extends bas. And then there was a one-element cache for the supertype. So if first time I asked, is bar a supertype of foo? And the answer is yes, and I record that in the cache. And then the next time another thread comes along and asks, is foo an instance of bas? No, I don't know, because the cache doesn't say that. So you have to look at the class hierarchy, and then yes, and then you overwrite the old value. So we will get this kind of flip-flop situation, especially if you're running code on threads that sits on different NUMA regions. So this kind of created a very bad behavior. So instead, we implemented an immutable lookup table, which is slightly slower if you compare to hitting the cache directly, but it has a much more predictable behavior, and it's much more lean on multi-thread applications. And this was introduced in JDK 23 for the bigger platforms, and the kind of more scarcely used platforms also got this in JDK 24. And the C1 still uses the old solution, but I don't think that's a big thing. Okay, string concatenation is another thing. The objective with this was not to improve performance, but to improve startup performance. So that's a different category. So here I have two different concepts. I have int bits equals 8, and then I have something that prints. In the 80s, many computers had 8-bit CPUs. So it takes a string, an int, and a string, and it concatenates them and produces another string. Now there is a completely different area, which says that I have a QNH equals 1013, and then I print the standard atmospheric pressure is 1013 hectopascal. Now, the shape of this kind of string conversions are the same, even though they are reasoning about completely different things. So what will happen now is that before we have something called method handle combinators, and the method handlers are kind of Lego building blocks that you can build on, but it takes a while for them to combine. So now we generate hidden classes directly, which has access to internals in a more efficient way. And then the classes were reusable. So if we go back to the previous slide, we can use the same generated hidden class for both those kind of classes. And this resulted in a 40% reduction in startup for the string concatenation generation, and also a 50% reduction in code generation, because we didn't have to use all these intermediary var handles or method handles. And the throughput was retained, so we had the same performance when we did the changes, but we got better startup. Okay, ZGC, generational mode by default. With ZGC, you can have much larger heaps. You can have heaps in the terabytes without having prohibitively long stop the world's events. And it was introduced, ZGC was introduced in 15. Then it got generational ZGC in 21, but it was turned off by default. And now in 24, the generational stuff is included there from start by default. And eventually, the non-generational ZGC will be removed. So look at, let this bigger circle here illustrate the heap. And the triangle and the diamond and the square indicates objects that we have on the heap. So now we create a new object here. And eventually that star becomes not reference anymore, and it will be garbage collected. And every time we have to check all the objects here. Now it turns out from common logic that the longer an object has been on the heap, the more probable it is that it will continue to stay on the heap, because most objects are short-lived. So then the idea is to divide the heap in two different generations. So on the left-hand side, we have the young generation, or it's not called the young generation anymore, but it's new objects. And on the right-hand side, we have older objects. And the idea is to check the newer objects more often, and the old objects not that often. So now when you create an object, it will appear here. And if it's dereferenced, it just got moved or discarded. But if it stays here long enough, it will be moved over to the older generation. And this gives the garbage collector much better performance. Okay, compact object headers is another one. This is an experimental thing that we have worked with. And every object has a header which you don't see from Java. So the idea here is to reduce it from 96 to 64 bits, or from 12 to 8 bits. This might not sound a lot, but when you have millions of objects, it's a big difference. So a typical object is around 256 to 512 bits, which is 32 to 64 bits. And that means that you will have 20% of your memory will be just object headers. So for example, if you go from 96 to 64 bits, you will use, we will have at more than 10% less memory. And in real world testers shows that we'll end up having minus 10 to minus 20% memory usage using compact headers. And it's not only about memory size, it's also about cache efficiency. Because everything is smaller, it's more likely that they will, emerge somewhere in the cache. And so the performance will also improve of the program that you are running. So that's that. That's the 5. I think it was 6. So now we go to future improvements. So we have product laden, which I spoke about yesterday, where we can store ahead of time classes and linking in a separate file that we can just boot from that file, and we can reduce the startup times by a factor of 4. Excuse me. Product Valhalla is another one where we can use flat representation. Let's say you have a point of int x and int y, and then instead of having an array with a secondary level of indirection, you can just flat them out on memory. And that will, of course, improve both performance and memory usage. And there's a series of YEP that's coming out now. And then we have the Vector API, which has a record of incubating 9 times. And the reason for that is that we are waiting for Valhalla to stabilize because they share a lot of common ground, and we don't want to, write the same thing 2 times. Product Loom is another one. We are improving the way virtual threads are handled. So we have now synchronized virtual thread without pinning coming up recently. We have stable values, which I spoke about a few hours ago, where the kind of war cry is codes like a lazy initialization, but performs like a constant. So this kind of gives you something that sits between a final and a non-final field. You get the both benefits from both of them. You get constant folding, but you don't have to initialize them up front. Then we have stream gatherers, which is a thing Victor worked with. And then the stream gatherers can many times be faster than the built-in operation of streams that we have today. And we are working continuously on improving performance with Java. And how do you test the application? Well, you can go to jdk.java.net and download early builds with Laden, Loom, and Valhalla, and also the latest version of JDK 10.4, and run your code and your application there. So with that, I would like to thank you for coming today, and yeah, nice to see you. And if you have questions, I'm happy to answer them now. Yes, one there.
Can you zoom in on that long to int? Why the long loop is longer?
The long to int that we have. The question is, can you zoom into the long to int? I guess you are talking about this one. Yes. Okay. So the idea is instead of iterating with a long index, you iterate with an int index, and that is just a part of the long indexation. So you have an inner loop that is using an int. And because the CPU can handle 32 bits more quickly than 64 bits, this is faster. So that is the idea with that. More questions? Yes?
How did you solve the synchronization in virtual threads? Was it just like a re-implementation, or is it JVM magic?
Yeah, the question is, how do we solve the unpinning? And I can't answer that question, I'm afraid. Yeah. Okay, more questions? Yes?
I actually made a mistake of using current time millis for performance tests, and it always worked until I started working on a Linux VM, and then it had 11,000 milliseconds and it went back every time, and that was really consistent. Is it a bug, or is that something that...
Okay, so the question is, I used this system current milliseconds, and it was kind of unpredictable. Is that supposed to be like that way? And the answer is yes, it's supposed to be like that way. It's not, the objective is not to punish you, but it reflects the current time in milliseconds. And that can be adjusted by a network time protocol, for example, which or you...
This was consistent. If I did it 1,000 times, then every
Okay. Oh, okay. I don't know. But the tip is to use nanotime instead. But I can't answer why that happened for you exactly. But it's very unpredictable, so don't use that in your benchmark tests. Okay, more questions? Yes?
Yeah, you briefly mentioned how you're focusing understandably on the architecture ARM64 and x86.
Yes.
You kind of threw RISC-V in with one of the tier 2 architectures, but it is gaining in popularity. So are any plans to start promoting that to a tier 1 architecture?
Yeah, I think eventually we will see a more adaptation of RISC-V, and I think certainly we will get them into our benchmark kind of pool of computers. That's for sure. So the question is not if, but the question is when. Yeah. Okay. Last question there.
What's the function of these headers?
What's the function of these headers?
Yeah, the ones that are becoming smaller. What do they do?
Which headers?
Yeah, Project Lilliput.
Ah, okay, those headers. Okay, yeah, that's a good question. Why do we have headers in the first place? That's a good question. So the headers, they kind of describe what is the class of this object, and it keeps track of the hash code. For example, if you have the system hash code, you know, it says that basically this is the address somehow, but it's not really the case because the address can actually move. Yeah, the GC can move your object around, and so when you have, for once, asked for the hash code, which is not, is using this system hash code, you need to record it there because it needs to stay the same all the time. Then you also have some bits for the garbage collector, so the garbage collector can see. Can paint the object and see, have I visited this object or is it an old object, and so on. And there's also more to it. If you have synchronization on an object, you have to have some kind of extra knowledge so you can inflate that and have it point to another structure that it's actually describing your synchronization. So that header is used in many ways. So it's a very good question. Thank you. Okay. Thank you, everybody. Thank you.
All systems are nominal. Initialize Genesis sequence.